Hello everyone, I'm Xingxing Zhang from Microsoft Research Asia, and today I will introduce our work, HIBERT, document level pre-training of hierarchical bidirectional transformers for document summarization. This is joint work with Fuzhu Wei and Ming Zhou. Okay, so this work is about document summarization. So what is summarization? For example, you have a news document like this, which is very long, and I cannot even fit it into one slide. The task of document summarization aims to rewrite a long document into its shorter form, for example, like this. You can see from the summary that this is the football match between Manchester United and Leeds, and Manchester United win. And these four guys kicked 4 goals. Okay, here's the task. And many paradigms for summarization have been explored. But the most popular ones are extractive summarization and abstractive summarization. As its name implies, extractive summarization extracts or selects the most important sentences in the document as its summary. It will not involve any kind of rewriting, so the grammaticality of the resulting summary is guaranteed. The most effective approach for extractive summarization are mostly based on hierarchical convolutional neural networks or long short-term memory networks. And our work belongs to the extractive summarization. Abstractive summarization are mostly based on sequence-to-sequence learning, where they view the document as a sequence and its summary another sequence. Although seq-to-seq model is powerful and augmented with copy mechanisms and also reinforcement learning, but still there's no guarantee that the resulting summary are grammatical or convey the same meaning as the original document does. Okay, this is the overview of our extractive summarization model we use in this paper. It's based on hierarchical transformers. We use transformer instead of CNNs and LCMs because we obtain a better performance. We have a sentence-level transformer encoder to learn the representation of each sentence in this document. We use the representation as the US token as the representation of a sentence. After we obtaining all the representations of these sentences, we have another transformer, the document-level transformer, to learn the context-dependent representation of one sentence given the whole document as a context. And lastly, we predict whether this sentence is a summary or not based on the representation. We train this model using the extractive labels, but unfortunately, in most summarization data set, extractive labels are not available. They are created by rule-based methods, and they are not accurate and noisy. Training such a complex model with noisy training signals is not optimal. And we believe training signals from other angles should be helpful. Given the recent success in pre-training NLP models, we believe pre-training hierarchical transformers, in this case, that's our document encoder, may help. The problem is how. Okay, let's first recap what has been done for the pre-training of non-hierarchical encoders, that is the sentence encoders. People try to use language modeling as a training objective, which is that to predict the next word given all the preceding words, or predict the previous words given all the words after it. For instance, MO is such an example using 2 LSTM language models, one is left to right and the other right to left, and GPT is left to right transformer models. But there's the one drawback of this kind of models is that during training time, they can only leverage the context from one direction. But during during test time, in many tasks, they have the context from both directions, but not well used. Based on this observation, Devlin et al. Proposed a BERT, which is based on the master language modeling training objective. The pre-training method works like this. For example, you have a sentence that, wait a second, we randomly mask some of the words in this sentence, and then we feed the sentence with masks into a transformer model, and then predict the master word, in this case, wait. By using the context from both directions, this kind of model can obtain better performance compared to left to right or right to left models. Of course, we want to keep this advantage in our model, but we also want to make this model hierarchical since document is in its nature hierarchical. Okay, our model is called HIBERT, which stands for Hierarchical Bidirectional Encoder Representations from Transformers, the hierarchical BERT. How do we train it? Actually, it's quite simple, that you have a document, and then we randomly mask some of the sentences in the document, and then we try to recover it. In this example, we masked the third sentence. We first use the hierarchical encoder we have introduced earlier to go through this document, and then we use the representation as the masked sentence 3 to predict the original sentence 3, one word at a time, until we met the US token. Okay, that's for the training. Actually, it's quite simple and straightforward, but also works well. Now I'm going to give you guys some details of how we do the document masking. For example, we have a document. William Shakespeare is a poet. He died in 1616. He's regarded as the greatest writer. Okay. Firstly, we randomly select 50% of the sentences in this document. For example, the second sentence is selected. Then we will do one of the 3 transformations below. The first is the mask. In 80% of cases, we just mask the select sentences. And we replace each word in a selected sentence with a special mask token. And the second transformation is keep. In 10% of cases, we just keep the selected sentence unchanged. Because during test time, we will never see the mask tokens. We just want to simulate this kind of environment. And then in the rest 10% of cases, we replace the selected sentence with a random sentence. This is like to add some noise during training and intend to make this model more robust. Okay, here is our model. And now let's go to the experiments. We train our model on 3 data sets. The first data set is the gigawatt dataset, which contains 6.6 million documents. That's a very large data set, and we use it for pre-training. And there's also 2 summarization data sets, the CNN Daily Mail dataset and the New York Times dataset. We created the New York Times 50 dataset following previous work that we remove documents whose summaries are shorter than 50 words, because if a document has a very short summary, extractive models just can't get a reasonable performance. Okay, now here are some details for our training. We have 3 training stages. In the first stage, we will do the open domain pre-training, which use the HIBERT objective we have introduced earlier, and we train this on the gigawatt data set. That's a very large data set. And in the second stage, we will do the in-domain pre-training on the training set of CNN Daily Mail dataset or the New York Times 50 dataset. And lastly, we will do the fine-tuning. In the first 2 stages, we will not use the information of summary. We just use the documents. And in the last stage, we do the fine-tuning on the CNN Daily Mail dataset or the NYT 50 dataset. Here are more details of our training. The batch size is 256 documents, and we do the open domain pre-training for 45 epochs, and 100 to 200 epochs for the in-domain pre-training. We have 2 settings. The first setting is the transformers in the first setting has 6 layers and the hidden size 512, and the second setting, HIBERT M, is slightly larger, that the hidden size is 768. And our HIBERT M can be trained on the gigawatt data set with 8 Tesla V100 GPUs for 20 hours per epoch. And the open domain pre-training is kind of computational takes a lot of computational cost. That takes around 35 days. Okay, here are the results on the CN-DailyMail dataset. We compared our model against the best abstractive summarization model, DCA, which is based on deeper communication agent. And we also compared our model with neural MMR. And it is the best extractive summarization model. We also built a BERT baseline by ourselves, simply feed a document into BERT, and using the representations at the end of a sentence token and do the prediction whether this sentence should be returned as summary or not. Actually, we are surprised to see BERT beat all the previous models. And we also have another baseline that is just use the hierarchical transformers we have proposed at the beginning of the talk without doing any pre-training, just use the extractive labels, and the performance is not good. But after doing the pre-training, our model, HIBERT S, outperform all the models in comparison. If we make the model larger, it can obtain even better performance. And I want to the trainable parameters in BERT is 110 million parameters, but HIBERT S only has half the size of the trainable parameters. And here are the results on the RUG1 and the RUG-L. They have the similar trends. In summarization, we usually report RUG1, RUG2, and RUG-L. And here are the results on the New York Times 50 dataset. We compared our model against the GECS, which is the model that first do the extractive summarization, and then they will compress the extracted sentences. And again, BERT outperform it, and hierarchical transformer model didn't work very well, and HIBERT outperform all the models. And finally, we also did the human evaluation on the CN-DailyMail test set. We have 6 baseline, 6 models here. The first model we compare is these 3. Just simply pick up the first 3 sentences in the document. And the second one is DCA, abstractive model. And the third one is latent, which is the latent summarization model we have developed in last year. It's an extractive model. And the BERT and HIBERT M. And lastly, the human reference as the upper bound of this task. We asked the subjects to rank the output of the 6 models. And we can see that HIBERT M obtained the best mean ranks, lower is better, and compared to other models in comparison, except for human. And the differences are significant. Okay, here comes to the conclusion. The core part of a neural extractive summarization model is the hierarchical document encoder. And we propose a method to pre-train it on unlabeled data and then fine-tune it on the in-domain summarization dataset. And experiments show the pre-training method is effective. And in the future, we are interested in to apply HIBERT to other tasks that also need document-level representations. And we are also interested in improve the architecture of HIBERT and propose new and free pre-training tasks. Okay, that's it. Thanks.